All right. Hello, everybody. I just got the thumbs up that we could begin. And I mean, I have a script here, but I just played with one of these robotic tools and it just blew my mind. So I think you guys are in for a very, very special treat. And hopefully you have an opportunity to play and try some of these very exciting tools. But welcome, everybody, to the High Weekly Research Seminar. I'm Nestor Masley. I'm a research manager at Stanford High. And today I am incredibly thrilled to introduce our speaker, Dr. Usama Khatib. Dr. Khatib is a professor of computer science and the director of the robotics laboratory right here at Stanford University. His research in robotics focuses on novel control architectures, algorithms, sensing, as well as human-friendly designs for advanced capabilities in complex environments. And his group is also exploring applications in healthcare and wellness, industry and service, farms and smart cities, as well as, and I think this is personally the most interesting for me, dangerous and unreachable settings, such as deep in oceans, mines, as well as space. Now, in today's seminar, Dr. Khatib is going to discuss Ocean 1K, which is a robotic diver that has a very high degree of autonomy for physical interaction with the environment, while at the same time being connected to a human expert through an intuitive interface. And the robot was recently deployed in several archaeological expeditions, which allowed humans to distance themselves physically from dangerous and unreachable spaces while still connecting their skills, intuition, and experience. And I think this is an example of some of the very exciting research work that we like to feature at High, work that bridges human as well as computer elements. Now, before we begin, a few logistical details. For our Zoom audience, you can use the Zoom chat to message the group, but we would ask that you guys pose all of your questions via Slido. And you can click on the link that will be posted in the chat shortly. Slido has a very nice upvote feature, which will allow me to prioritize the questions that we want to pose afterwards. And after the presentation, we're going to be switching off between questions from our live audience who are with us today and questions from our virtual audience. Now, with that, I would like to welcome Dr. Khatib to take it away and to wow us with these robots.
Thank you so much for this kind introduction. It is a really great pleasure to be here at High. This is a very familiar place for me. This is where the robotics lab was until probably 2-3 years ago. And we are so happy to see High here. The robotics labs are actually on the second floor. And the robotics labs have much more robots and much more space. Little later, I'm going to take you to the lab, and we are going to do a premiere trying to control a robot to do ultrasonic imaging from here with this haptic device you can see just next to me. So remote interaction with robots is a very important field as robotics moves to the real world. Romeo and Juliet are actually were part of this effort, and I will be talking about Romeo and Juliet and how Romeo and Juliet led us all the way to Ocean 1. But Ocean 1 is one of the few robots that is going to work in those extreme environments, connecting humans, that is like those of you who have touched virtual environment. We are going to work with a robot, and when this robot is going to touch the seabed, you are going to feel what the robot is doing. You're going to be able to help this robot. And this is what we've been doing. And last year, we ended a mission last July, and that mission was to take the robot slowly from 40 meters all the way to the bottom of the sea, where we can still operate the robot to perform tasks that requires hands and requires sensing and requires retrieving artifact. So this robot comes following the original Ocean One. Ocean One was designed and deployed in 2016 to retrieve artifacts from La Lune. La Lune is a vessel of King Louis XIV that sunk off the coast of France in 1664. And it is at 91 meters, but it's very difficult to reach the boat because humans are able to go to 50, 60 meters. So to reach this boat, they use suits. And any interaction, normal interaction for an archaeologist with that environment is very, very difficult because you need to touch, feel, and interact before removing any object. So the concept of Ocean One is to create hands with sensors, and these hands are going to require arms. And now think about the problem of taking hands and arms and electronics deep in the sea. So the robot has to float, and this robot was conceived with design of flotations. For the arms, we don't want an arm that is heavy. We would like to have a gentle arm. We call it compliant arm. So that means we have to come up with a solution for the pressure. You don't want to use heavy metal to protect the arm. So we created oil-filled architecture to build the links. And through tubing, we go from one link to the other so that we can have a compliant touch-sensitive arm. So some of you have tried this. This is one of the most popular demo where you wear your glasses, you see in stereo, and you are able to touch the simulation. The simulation is very important for developing any complex system, and this was one of the tools that we used in our work. So this is not an animation. This is a physical simulation with dynamics. You can see this ellipsoid changing as the robot dynamics is changing as you extend the hand and move the hand. And finally, this robot needed to be tested. So we took the robot to the pool. And you can see the robot in the pool moving here. I'm not sure if the sound is coming out. So just maybe we can make sure that we have sound from the video. And students will be sitting by the pool watching the robot or swimming with the robot. And it was a lot of times of taking this robot all the way to the pool and testing this robot. And finally, the robot was ready. We shipped it to France, and we were deploying the robot on the site. The robot was tested at 15 meters first, interacting with human. And then we took the robot to La Lune. Now, on La Lune, this is a 4th century old boat, so the whole boat disappeared. What you see here on this image, you see part of the cannons that remain, and our colleagues, archaeologists, wanted us to go between them and retrieve some artifact. And that was an amazing experience for us. We take the robot from 1 meter here in the pool to 91 meters, and the robot kept same controller. We had to adjust for the flotation, but we encountered a lot of surprises. Currents can push you, and you can get the robot stuck between the cannon, and you can see the face of Hannah praying when we had this problem. But with haptics, you can solve any problem, because with haptics and the arms, you push yourself and you free the robot, and the robot was back to recover artifact. So what you do is you place your artifact in a container that floats on its own, and you can see my students so happy. We recover a vase. It's a Catalan vase from 1664, untouched by a human, and unbroken. And the archaeologists were really amazed. I mean, this is amazing, beautiful vase. You didn't scratch it. How? This is because we have dexterous hands, and the touch is so gentle that you are not going and smashing the artifact that you are collecting. The year after, we took the robot to another nice place, Santorini. I mean, this is a tip to the students. Make sure your robot goes to nice places and then just follow the robot. So we were working there with scientists, and we were supporting the work of scientists. It was not about the depth. It was more about how robot can interact and work with human. We don't have too much time to talk about every expedition. I'm going to move to the question, what is the relation between Romeo and Juliet and Ocean 1K? Well, I mean, it wasn't like one day we woke up in the morning and say, okay, let's build a robot to go underwater. I mean, it was a long, long process that took us to come with this idea and come with the capabilities to handle pressure underwater. So in this place, actually from here, the camera is over there. You are seeing the inauguration of the Gates building. And this was Bill Gates with Melinda Gates. And my students were demonstrating this robot over there. This is the Romeo. Juliet actually is at the museum now in Munich. So Romeo is alone in the lab. So I mean, this was amazing because when you think about it, it's 1995. In 1995, we were able to iron, vacuum. We were able to get robots to cooperate. And with a very fragile case, I mean, this is amazing. Even dancing with the robot. So I will show you more a little later, but robotics has evolved so much since. And today we have so much progress in robotics. And this progress is quite amazing, especially when we think about mobility. I mean, in mobility, we see robots on land, in the air, underwater. The challenge that we have today in robotics is, can we do the same progress with physical interaction? That is, with robots that are able to interact with the physical world and not only see and move in the free space. So just think about a task like this, cleaning solar panels. This is very difficult because you cannot anymore pre-program the robot as we did before, inspired by the assembly line. I mean, with the assembly line, we automated the process where we design fixtures and jigs and make sure that everything is capable of going over and over pre-programmed. Well, now we are talking about robotics in the real world, unstructured environment. And if we cannot program these robots, how these robots are going to be deployed and operate in real time? Well, humans do it. And humans are very different from the robot we use in manufacturing. In manufacturing, we use very heavy, bulky robots because we wanted precision. Humans are not precise. So the only way we can do that is if we come to an abstraction of the way we program robots. If we can bring human skills to these robots and ask the robots to perform high-level tasks. We don't need heavy and rigid robots, but we need what humans use, which is the touch. We compensate for our inability to be precise with our touch and feeling the way to the task. So this is the compliant robot, and you can see here an example of compliant robot. There is no trajectory. The robot is feeling the contact. The reaction forces are guiding the robot in the proper direction to achieve face-to-face between two objects. This works also in dynamics. The environment can be moving, and the environment is going to change the direction of the reaction force, and the robot continues to implement a strategy to achieve this goal. So this is something very important, human skills, understanding human skills and trying to build manipulation skills. And the human is an amazing model for us to learn from. But the way we try to learn is really a model that is relying on understanding what is going on, not just going and recording trajectory and try to interpolate between these trajectories. What we would like to see is what was going on in terms of the strategy, the human strategy. So objects can be defined with a frame. And if we take the data after segmentation and project it on those frames, we can understand what was the compliant frame, and we can describe what for this task the strategy was, and encode the strategy to the robot, and then implement it of the robot. So here is an example. The same haptic device is controlling a robot to perform this task. And as the robot is learning the task, now the robot can reproduce the task with the strategy. This is implemented in many different, this is a model of the wing 787 wing, and you are placing this piece at this location through a strategy involving compliant motion, and you disturb the robot, and the robot will find its way autonomously, because it is relying not on the trajectories, but on the strategy of compliance. You can teach robots to do all kinds of tasks, including the fact that you also need to teach robots how to use two hands. In manufacturing, we use one hand because we have fixtures. If you place your arm behind your back and try to move it and work in the real world, it's very difficult. So the other thing about those architecture that we use, these are not only relying on one loop feedback between perception and action. We need to deal with the frequency requirement of the system. Mechanical system requires high bandwidth feedback. And that is the lowest level should be controlled at very high frequency. But we don't need the same frequency to understand the features of the objects we're working with. The input to that level is going to be much slower. And as we move up in that hierarchy, we are going to have a multi-layer system that is answering the requirement in frequency to achieve functional autonomy. We still don't have the cognitive autonomy, and we are going to rely on the interface so that we bring to the human an interface where the human can talk with the robot through speech or through haptic interaction or through programming to perform a task. A very important tool, as I mentioned earlier, is a physical simulation. Physical simulation, we saw how we can simulate a complex robot. This physical simulation is very important also because it requires us to think about the contact. Simulating contact is very difficult. Simulating multi-contact is even more difficult. You see these reaction forces, the red flash that are coming out from the contact. If any of them would go outside of the cone of frictions that you see, well, we're going to fall. That means the robot has to apply different forces as the environment is changing. And this is possible if we bring these physical models to the system. Actually, this was implemented at DLR in Germany with a robot called Toro. Implemented for many robot Ocean Ones to perform pipelines in different tasks. Actually, this is was a fantastic tool that we provided our students during COVID. Typically, during this class called Experimental Robotics, we do real implementation on the physical robot. And this is an example of a robot fighting. And with Psi, we were able to get the robot to perform tasks for the student project. And the students always are hungry, so they are making projects with food. And I would like to have the sound again, please, because the next segment, if we can have the sound. So this is another example of dancing Toro. And this is an amazing one. Two robots playing ping pong. Have you seen two robots playing ping pong? Well, this is physically correct. This is simulated robot contact with everything. But at some point, the loser can get angry. See that other player is very successful. All right. So we are inspired by human, but we also are able to take our algorithms and apply them to humans for human performance, for human recovery. And there is a huge amount of work that went to building atlases for different human in their activities for recovery or for performance improvement. So robotics in the field addresses many different issues, from healthcare to wellness, from assisted work to assisted living, and all these other things that are difficult to perform by human or dangerous for human. So this collaboration with human can be done directly by interacting physically with the robot. Ashimo was here for almost 10 years. And Ashimo graduated and left with the capability of becoming capable of feeling and interacting. Actually, if you look closely to Ashimo, Ashimo is surprised now, because what is happening to me, in the past, Ashimo didn't have any feeling about any contact. And we equipped the robot with force sensing, so it feels those contact information. Now, the contact information can be brought to the human through haptics. And there are so many applications where we can use this to save human from exposure to danger. Like if we think about the electrical grid, do we really need the human there? Can't we place a robot there and then reconnect the human to perform and assist the robot with the task? This is an example of removing a cable, and you can see the robot is performing this with its own force sensors, and the human is providing corrections when needed. You can do it in the air. You can do it in the ICU. In the ICU was really a challenging problem. I mean, you just to do the simplest procedure, you need to wear all these gears, but we can place a simple, safe robot connected haptically to a physician, and now we remove physically the physician, but we reconnect the physician abilities to perform this task. Actually, I'm going to show you this live now. We're going to look at another application with ultrasound, and I see Adrian is standing up. And we're going to do first, we're going to go to the lab, and we're going to control a robot over there in the lab using a haptic device like here. And we are going to be able to see live the display, the imaging, ultrasonic imaging from the robot. This was done
center over the right portal vein, which is our third anatomic
colleague in the
landmark. You can see it right there in front of the inferior vena cava. And you can see the right portal vein divides into an anterior branch, and if I angle more
we are
a posterior branch. And so there's the right portal vein dividing into an anterior and a posterior branch. And I'm just going to extend my scan more inferiorly and look at the more caudal segments of the right lobe of the liver. And now I'm coming into the gallbladder.
You ready? Oh, wow, it's moving. So So Adrian, who's a very smart PhD student, is now performing radiology. And Adrian doesn't have the microphone, but essentially he is working with this phantom, and the phantom has different organ. And we are, which organ we're looking at here? That's what I thought. So what are you looking for when you look at an organ? Adrian.
Right.
Yeah. So when, yeah, just stop here. You can see here, you can see this like high density image, and that tells you there is a problem. So the idea is now we are controlling remotely the robot. Adrian could be in New York controlling a robot in a different city on the West Coast. And that means now we can think about distance medicine, where in many small towns there are no hospitals, but we can very quickly deploy testing facilities with a technician, and then we can, when needed, reconnect to a hospital, and the doctor can perform a deeper test and look at what is going on when we detect any anomaly. So thank you very much, Adrian. Another application is in construction. In construction, there are so many applications that you would like to automate, you would like to use robot force. And over the several years, we've been collaborating with the civil engineering, looking at drywalling, at painting, at bolting. And in every area, we had a project, either a project in class that ended up to be a project of research. And all of these different projects are quite interesting to start to explore how we bring robots to those challenging areas. Now, offshore robotics is another important area. I mean, on offshore, we have humans doing very simple tasks. And those tasks involve opening a valve, closing a valve, doing a measurement. We can deploy a robot to do this, and we can replace humans onshore to help this robot performing those tasks. We can use the robot for many things, including art, painting, sculptures. And there are many projects around how we use haptics interacting with the physical environment to perform many challenging tasks. So all of this brings us to Ocean One. Ocean One wasn't just on its own came as a project. Most of the foundations came before we developed all these foundations, and we deployed Ocean One, the first robot. Ocean 1K was a big challenge for us. We wanted to go really to the deep sea. So going from the first robot that has managed to go to 91 meters to go to 1,000 meters means we are going to make sure that the flotation is not going to collapse. At 1,000 meters, you have 100 times the atmospheric pressure. It means with these flotations, you are going to basically increase the density, which means you're going to increase the weight, which means you're going to increase the volume to float, and maybe will not fit in this room. I mean, it would be really, really difficult. So what is helping robotics is the convergence of technologies in computing, in material. In material, we have found that there are new kind of syntactic foams that are essentially hollow microspheres that are very light, that they are very strong when they are under pressure. So actually the robot was this was during COVID, and we were assembling the robot to get it ready for the expedition that took us to the Mediterranean, Marseille, and Corsica, in collaboration with our colleague at DRES from the Department of Archaeology at the Ministry of Culture. First, we wanted to go 40 meters and go deeper and deeper. We went to the Lightning. The Lightning was one of the combat aircraft during World War II, flown by Saint-Exupéry. Then we went to another location deeper, Le Protet submarine. And 2,000 years ago, there was a Roman boat at Aleria at 334 meters. And this boat has completely disappeared, but all the cargo is still there. Le Francisco Crispi is a wonderful, incredible backbow that was shot by the British during the war, and it is a site full of unique marine biology with rare white corals. The robot was training. The robot was learning how to use tools to do scanning, to make videos inside structures that are difficult to access by the robot. So the robot is able now to manipulate a camera, and this camera is possible for using. The robot is also interactive, support human. And here we came to our location where the boat was waiting for us, to La Ciotat. La Ciotat is a small town near Marseille. Anyone knows La Ciotat? Not Adrian. Adrian knows La Ciotat because of this. You remember Eden? So those of you who likes cinema, the first movie theater was here at La Ciotat. Les Frères Lumière came to La Ciotat to film, and this was the projector in the cinema that's still standing. And if you go to Marseille, don't miss La Ciotat. This is our boat waiting for us at La Ciotat, l'Alfred Merlin. Our robot arrived on the boat, and here we have the robot installed on Alfred Merlin. Alfred Merlin was a new boat for the Ministry of Culture. Look who came to visit. The President Macron was there, and he was really very interested in the haptic interaction with this robot. A few days later, my students arrived, and we were ready for the big dive. And to dive, you have to realize you're going for 7 hours in the water. So you need a lot of support with cables, and you need power. You need to film. So there are a number of rows that are moving with you. This is the control room. And we went to the Lightning. We went to Le Protet, and then to Corsica and Aleria there. Aleria is just an amazing location. Here is one short view of the robot going to bring a cup. Here is the cup. I mean, the archaeologists were so happy we were able to bring a cup without breaking it. This is so fragile. It was studied. They had it in images, but never get their hands on it. And we brought all kind of artifact, including oil lamps. The oil lamps decorated with the palms, different decorations, and a lot of shrimps came with the robot. So then we went to the Crispi, and the Crispi, the first task, we place a marker, and once you place the marker, then you can go and scan, and then you can have a 3D reconstruction of the actual boat, and then you can go around it. And we will see the expedition on the Crispi just in a moment. After that, we went back to the coast, specifically to Cannes, and we went with the camera to film inside this airplanes. And you can see the robot going inside with the camera and filming. And what we discovered that is that Cannes, I mean, everyone knows Cannes for the film festival, but but Cairn has also the Himalayas downward, and the Himalayas goes very, very deep. So our robot went from our record was 500 meters for the Crispy to 750 meters, and kept going, carrying a message that says a robot first touch of the deep sea floor, a vast new world for human to explore. And I said, we won the Palme d'Or. So let me show you. So you have to remember that all of this cannot be done just with a small group. It requires a huge crew to take the robot to those locations, to help with deploying the robot in the water. And you can see on the right all the crew, and on the left my students and collaborators. So I wanted also to mention that all the difficulties of taking this robot and testing the robot over in the pool, what we were able to do then is going to be much easier with something new taking place at Stanford. And this is the Stanford Robotics Center that is going to have an aquarium. This is the aquarium at the end of the center that is going to be just next door. And the aquarium and this center is designed to bring faculty from all the different departments across Stanford to bring this multidisciplinarity to what is needed for challenging tasks. And here, all my colleagues who are part of this effort. And our vision is to take the center to create a bridge from research to real world applications in those very important 4 areas of field robotics, future of work, education and culture, and health and wellness, with flagships that will be implemented in physical space with the robots in collaboration with corporate members that will be actively involved in those efforts, and with outreach and also something that our students would love to have, which is real interaction with more physical robots. So the center is being built right now, and just a few days ago I was there, and you can start to see the sky coming and everything. So I hope this will bring a lot of excitement to robotics at Stanford. Thank you very much for your attention.
Thank you very much for an excellent and super fascinating presentation. So for the audience that is in person, we have a microphone right there on the right side if you guys want to get up and post some questions. And for the audience that is on Zoom, again, we would ask that you pose your questions to Slido. And we'll start with a question from a Zoom audience member who comments on your technology being quite incredible, but asks, how do you respond to the argument that advances in robotics could replace many human jobs?
Well, thank you for this question. This happened actually in the transition during manufacturing, during the revolution of manufacturing that brought robots. Basically, we created spaces where only robots are working without the human, and robots and human were separated. Working in the unstructured environment of the real world is a much more challenging problem. And you can see that in every aspect of interaction, we need the interface to connect to the expert, to connect to the specialist, who is to connect to the archaeologist, to the physician. And I don't think in those applications robotics is going to replace human. It's going to bring to human more capabilities and tools to interact and reach places that are difficult to reach. Right now, 70% of our planet, which is covered by water, is unknown. And we have so many challenges with the environment. How can we understand the oceans without tools to go there? And it is not about just looking and seeing with cameras. It's about doing, maintaining structures. So many things in different areas that are very difficult and challenging are going to require human intervention. So we hope that this is the direction that robotics will take.
Great. Let's go to the next audience member for a question.
I was more like abstracting from, not from diving. It's not only interesting for diving. I think it's also interesting for protheses. So there are protheses out there that basically have these touch sensors. And I was wondering, I always see these joysticks, but there's also like these electrodes directly connected to the human being. And if there's like interest into the developing like a control device that is more like connected to the human and also makes the control of the robot more simple, because it feels like a little bit unhuman to have like these joysticks on. That was one thing that I was thinking of. If you also go more like into this direction, helping like the human being with your robotics, and also using existing prothese techniques that are there for like tactile, thank you, tactile touching for like disabled people in your work here.
Thank you so much. There is no one robot that solves all these different problems. We are working in robotics, and I was just talking about one robot and maybe one past robot. But our work really is aimed at many different aspects, and this is why we have the center. The center is going to have multiple units and suites focusing on different aspects of robotics. And what you describe is something that we are very much interested in. We are making use of human motion, measuring muscle activities, and training people injured or athletes how to move. We have colleagues who are working on different devices to support human walking or to support human posture. There are a lot of things that robotics is teaching us to understand human motion. In fact, we are collaborating with BioX and with biomechanics, the group of Scott Dalp and others, in really bringing new tools, new computational tools, and new robotic tools, and in new metrics. So here, these are the maximum acceleration lines. If anyone needs help with the tennis or golfing, I can help you, because it has to be really specific to the person, and this is relying on your muscle and physical kinematics and dynamic characteristics, and all of these can be discovered and used to improve performance and address all the challenges in human. So my answer again, it's not only one solution. This is the only robot in the world that is capable today to go to the depth and retrieve things and repair and fix things. But we are working on many other robots, and we need many different robots. And when this robot goes to the sea, the bottom of the sea, is going with many other robots designed very simply for vision or for monitoring the configuration of the robot. So yeah, this is robotics. It's very, very diverse. So I mean, for handicap already there are so much. Oh, you're golfing. Well, I really can help you. I mean, this is amazing. This is telling you what are the line of acceleration, and you can watch yourself playing, and you see the corrections as you're playing, and you could train in the simulator first, and then. So we are open 7 days a week. Yeah, you had the follow up.
Have you how far are you from removing the cables for cave diving and stuff like that?
Moving the tables?
Cables.
Because
if I see it correctly, because what also interesting is communication wise underwater, it's more difficult.
Exactly. This is one of the big challenges with underwater robotics. You need a cable because you need the power. And we actually moved this robot in the pool with a battery, and the robot can move alone. I mean, you don't need to interact with it. If you have localization SLAM, you can do that. And we did it here, but the battery lasts for 40 minutes, so we couldn't even test the robot. So the power is one problem. Then the communication, you don't have electromagnetic signals in the water. And however, we worked with our colleague at MIT with the development of optical modems. So the communication problem is solved at a short distance. So what is happening right now, our robot is moving, multiple robots are moving, there is always, they are connected to another robot at 30 meters. So what the future will be is you have a cable to a station for communication and power, and you can have these 3 robots communicating through optical modem and recharging from that station. So there will be stations in the future next to your construction and sites, and the robots will be completely free.
I'm not sure for divers, there's like something you can basically put on the boat so that they basically have like an orientation to the boat. I'm not sure if that helps there too, but yeah, thank you for the answers.
You're welcome.
All right, I think we have time for one more question. We're going to go to a Zoom question. One of our Zoom users is asking, do you often work with medical professionals, environmentalists, etc., to help see new applications for this technology? And if so, what are some of the new applications?
Yeah, well, the medical applications are maybe one of the most difficult applications where we are really lucky to see that we have working robot today. I mean, there are 1,000 and 1,000, tens of thousands of surgeries done by robots today. And it doesn't mean we are solving all the different procedures. There are some procedures that are handled by robots, but there are a lot of other simple procedures that can be handled by robot. I mean, in a hospital setting, there are a lot of tasks that involve services, and all of these can be handled by robots together with personnel. But the key aspect of robotics in medical application is safety. And one of the things that we have been working on for years now is how to develop a robot that is completely safe, guaranteed to be safe. So guaranteed to be safe not by your computer that could have a small glitch and fail and the whole safety is gone. We want to make sure that the safety is mechanical safety, it's passive safety. So among these guys sitting here in the front, there are some people working on this problem with some really exciting new solutions to this aspect of the robotics in medical applications. We are working on bringing very lightweight, very dexterous, very simple robots that can perform very light and simple tasks that are needed, but also reflect those interactions to a human through an intuitive interface. And this is something that I think is going to come in the coming years, and it's going to be very important for this idea of distance medicine, because distance medicine is going to allow us to reach, especially in the developing world, to reach towns and villages where there is no coverage of hospitals and medical facilities. And this will reconnect those places to hospitals through those interactions. But locally, most of the work can be done to scan, and just in the cases where we need to perform. So we have some collaboration with a group to explore how we can deploy that for pregnant women examination. We have other collaborations in those domains. And robotics can be really a wonderful solution if we satisfy all these safety and simple characteristics that is needed for their operation.
Well, thank you very much for this fascinating presentation. I mean, it's super cool to see firsthand what some of this technology is capable. As a fellow golfer myself, and very bad golfer, it hurts me that robots can probably play golf better than me now, but I suppose that's just how technology marches forward. Thank you to everybody who was on our Zoom audience, and to everybody as well who showed up in person. And again, thank you, Dr. Khatib, for a fascinating presentation.
Thank you. Thank you very much. Thank you.